That disc or that tape?
Tape.
Oh. Don't they make them a little bit like?
I don't know where it is.
Variable volume. This is obviously a single duct variable volume application. So in most cases you'd have here would be what we call medium pressure duct. And there. Most cases, this would be probably greater than 1,500 feet per minute, up to probably maybe as high as 4,000 feet per minute velocity. And probably ranges 0.3 inches to 0.4 inches water gauge per 100 feet of duct. There's different ways to size this kind of duct. The reason you have these high velocities in relation to velocities here, which we'll talk about, is that that duct just gets too damn big to fit in space. So you'll see a lot of duct, that size generally around the 3,000 feet per minute. That's pretty fast. It's pretty high velocities. High velocities cause high pressure drops. But you got to fit it into space. You got to fit it above the ceiling. So what you'll see in these types of fittings, you'll see, and generally this is the spiral duct that you buy pre-manufactured, or you can buy it, or you can build it. In the spiral duct, you'll see fittings that is called conical. So you got an airstream going down through here. That air has to turn and go out to a VEV box. And what it is, this duct may be 8-inch. And you have a slight wider opening so that the pressure drop, the velocity is slower here till it gets into this duct. And that fitting right there versus a fitting like that would probably have 4 times less pressure drop than a fitting like that right there. So you very seldom would ever see a straight tap like that on high pressure duct. And even the square built duct, you can build fittings like this. But in high medium pressure duct, it's very important to use what they call conical fittings or expanded throat fittings to reduce that pressure drop. And that pressure drop may not be very much, but I have seen applications in risers where you've got a riser going down that's maybe at 2,000 feet per minute or 2,500 feet per minute, and a takeoff coming off of this straight tap that might be as high as 1 inch of pressure. You may have a building like this that may be multi-stories. Each one of these is a story. And this works fine, can't get any air on this floor, and this floor works fine. And you generally trace it down to some kind of fitting in the duct that causes that pressure drop. It was constructed wrong, it was built wrong, designed wrong, whatever. But The supply duct in a BEV single duct application would be called medium pressure duct. These are the ranges, the pressure ranges that you size it by. And you have to be very careful with the fittings. It can be bought in spiral duct. It can be built. SMACNA, the sheet metal folks, have recommendations for fuel fabricated duct. You look at your pressure that you want to build it to. For instance, the engineers calculated this, and he said that this classification is probably in the 3-inch range, 3 inches of static pressure. And this is probably 1 inch static pressure. You know, the air handling unit may be 6 inches. But remember, we got coils and filters, things in here, and we talked about the difference between the positive pressure and the negative pressure. So this should be listed in the specifications, may or may not be, but a sheet metal man would go to his SMACNA book and say, I want to build this duct for 3 inches of pressure. And he'll have options of different gauges, 20 gauge, 18 gauge, 16 gauge, more like probably 20 gauge. And SMACNA will tell him how to build it, what kind of seams to make in it, and how far to specify his reinforcement. Reinforcement might be 4 feet on centers, it might be 8 foot on centers. And then you get to a certain size duct, I don't know what it is, but let's just say it's 4 feet by 4 feet. You may actually see 1/2 inch EMT conduit in this duct to stabilize the duct. That's perfectly legal. It's an appropriate design allowed by SMACNA, but it's just odd looking. And generally they just use 1/2 inch EMT conduit. But all of that has to do with the charts that are listed in SMACNA and how you build this duct. And it's based on the pressure range that you want to maintain, and then the contractor has the choice of what gauge and what kind of reinforcement that he wants to use. In square duct, someone needs to design these type of fittings, but generally it would just be an expanded throat type fitting. On the return side, we're picking up air on the return. That's generally going to be low pressure. And that's generally probably 300 up to 1,500 feet per minute, maybe 1,200 feet per minute, generally in the 0.05 to 0.08 inches per 100 feet of duct. So this is in 3/10 of an inch per 100. These are in 500ths to 800ths of an inch per 100. Consequently, the velocities are lower as well. In this high pressure duct, you're always going to have sound problems. Pressure generates sound. These boxes generate sound. So there's a lot of design that you have to look at on the supply duct we'll talk about in just a second. But all this generates sound, and all it has to be attenuated before it gets to the diffuser. This low pressure duct, you generally don't have to worry about sound except right here. The air handling unit generates a certain amount of sound pressure. Generally that's shown in the submittal documents. Looking at sound is very, very complicated in how you address it. Most people just look at the sound generated by the air handling unit, and they put silencers here or here in the duct, and a silencer is just an insulated piece of duct with a lot of insulated baffles that it generates or attenuates a certain amount of sound. Balancing techniques for the low pressure, generally manual dampers in major branches or individual branches to diffusers. You're going to have some kind of balancing technique to balance this air in this low pressure duct. And generally, like I said, just manual balancing dampers at major takeoffs or at the grills. In the medium pressure duct, you don't generally worry about balancing that duct because these VEV boxes do the balancing for you. Now, there's computer ways to generate this duct where you can actually size it to help balance it. Some people utilize that technique. Some people just use this manual sizing method here. But these VEV boxes, if they're sized appropriately and operating correctly, they're going to do self-balancing. And what happens, these are called pressure-independent boxes, meaning that the controls that you put on, the velocity measuring devices that are on the inlet of these boxes, measure the airflow, adjust these damper positions, maintain a certain amount of airflow, no matter what the pressure is. So for instance, if this box closes, and this box closes, and this box closes, this is the only box open. If you remember when we talked about variable volume piping systems, we had a differential pressure transmitter. That references back to just the open space. So we're measuring the pressure in this duct, just like we're measuring the pressure in the piping system. This differential pressure transmitter is talking back to this VFD, this variable frequency drive. So as these shut down, this differential pressure goes up, the fan responds, the airflow goes back down, pressure goes back down to the set point of whatever the differential pressure is. So that's how the supply duct is balanced. The return is just dependent on the fan pressure. We've always got to have enough pressure available to get the return back from the grill, just back through the ductwork and into the fan. Okay? VEV terminals. Nothing but a damper with an airflow measuring, some device that measures airflow, responds back to a control device, and a thermostat. Basically, that thermostat says, I want to maintain a certain temperature in the room. It responds back to its control device, and that damper modulates to maintain that temperature. Simple as that. This is self-contained. Doesn't really depend on anything. In the controls end of it, we're measuring that airflow so we can see it, we know what it is. You may also have a temperature sensor right here for diagnostic purposes. Let's look at a VEV box. Got a damper, got some type of device that's in this round opening right here. It's measuring the velocity and the pressure, converting that to airflow. This has got an actuator on it with a motor. And our ductwork going out into the space has a temperature sensor here. All this has a little bitty controller mounted on the box, some type of controller. But you pick up your static pressure and your velocity pressure, take it into this controller. It knows the diameter of the duct. It knows the velocity, so it can calculate airflow through here. And that's just an input. Now the reason it wants to calculate the airflow is you probably programmed a maximum and a minimum airflow in this box. So the engineer has said this space needs a minimum of 100 CFM and a maximum of 400 CFM. 400 CFM to meet the load in the space when the lights are on, all the people are in there and all the equipment. 100 CFM to meet the ventilation requirements. We talked about outside air, and the effects of outside air is to dilute the contaminants in the space. So you'll see these boxes generally never close unless it's unoccupied. There's all kinds of control devices that we'll talk about some other time, but to know whether that's occupied or unoccupied, it could be a motion sensor, it could be an occupancy sensor like a current sensor on a light to know the lights are on or off. But in airflow, generally you'll have something like this, something to meet the load, something to meet the ventilation requirements. So that's why this controller is measuring the airflow, measuring the velocity, calculating the space, or knows the diameter, calculates the airflow, and it's modulating this motor, opening and closing that damper to maintain the maximum and minimum airflows. thermostat in the space is doing the same thing. It's telling that damper, it's talking back to this controller, and it's saying, I need airflow. So it's going to open that damper up to its maximum set point. So as long as this is calling for air, meaning the temperature is out of set point, either above the set point or below the set point, whether I want to heat or cool, this thermostat's talking to the controller, says I need air, and I'm out of set point, the damper opens. Same thing happens in reverse. Temperature set point is met, maybe it's overshot, it says I don't need any airflow in the space, it talks back to the controller tells the damper to shut. All the time it's measuring the airflow and monitoring the airflow to meet its maximum and minimum. Temperature sensor in the duct is mainly for a diagnostic purpose. It's talking back to the controller, which the controller is talking back to the other controls. And for instance, if I get a hot call for a space, I'm an owner, pull this box up on the network, I can look at this. And this is 55 degrees and it's winter time, and all of a sudden I'm at 90 degrees here, but I'm supposed to be cooling. And that would tell me that my hot water coil or my electric heater's on when it shouldn't be on. But that's a single duct box. It has no reheat. So you can see if my minimum airflow is 100 CFM and I have no reheat, this is pumping out 55 degrees all the time because it's a single duct cooling only VAV system. My heat is dependent in these zones. And that's the purpose for these VAV boxes. They just create temperature zones in the space, control points. So, you might have it per office, you might have it for groups of 3 or 4 offices, you might have a conference room, whatever, but that VAV box is creating a temperature zone in the space. So if I've got the same thing over here, 100 CFM max, 100 CFM minimum, so what happens is I've got a coil right here, whether it's a water coil or an electric coil. So what happens is I've overshot my temperature, thermostat's telling the controller the space is satisfied, the controller goes to the minimum airflow. But it's still pumping 100 CFM at 55 degree air through there. So the controller then, its response back from the thermostat says, the temperature is continuing to drop, I need heat. Damper's at its minimum position and the valve starts to crack open to maintain temperature in the space. Same thing in reverse. It's too hot in here, the damper is going to go to maximum position and the controller is going to tell the valve to close. So that's how the VAV box cools and heats, just in response to that temperature sensor in space. This temperature sensor is just for diagnostic purposes. This controller is talking to a motor while it's getting the airflow. So that's a single duct VAV with reheat. That reheat's electric, it's hot water, might even be steam. Single duct VAV. Fan-powered VAV application, where I've got that same little device here, just that box with the damper in it. Introduce a fan right here. And it takes air from the plenum, the return air plenum above the ceiling, or it could be ducted to a grill. But it's just the space temperature, whatever the space temperature is, it circulates through this fan motor right here, mixes with this cold air, and delivers to the space. So why would I use something like that? Well, it could be that I have to maintain a certain amount of airflow in space. Okay? So this box is 400 CFM all the time. So what happens is, in this case, my damper's wide open or modulated to some position that gives me 400 CFM. I've got to reheat that 400 CFM right all the time. So from 55, probably up to room neutral conditions of 75. I'm reheating that air all the time. It's an energy waster, right? So I use a fan-powered box And the controller tells this box to close to 100 CFM to meet my ventilation. This fan operates at 300 CFM, circulating 70-degree air through the space. I'm still putting 400 CFM into space, but I'm mixing 55 with 70-degree air or 75-degree air. And so this valve is only reheating 100 CFM instead of 400 CFM. So that's the purpose of a parallel fan-powered box, is to generally save energy if you're trying to maintain high amounts of airflow in space. It could be that someone just decided that 100 CFM is just not enough to circulate into space. That's another reason to put in this. This may still be variable volume, but they want this fan to put more air into space. So this is called a parallel fan-powered box. The VV box and the fan is in parallel. This one's called series. We talked about series pumps and parallel pumps. These are series VV box in series with the fan, meaning that whatever this is moving, I'm moving it right here, but I still have the option of putting an inlet right there to mix cold air with my room air temperature. And again, this is probably some constant volume device. This is variable volume, but the fan's probably moving constant volume of airflow. 400 CFM. This ranges from 100 to 400. So it's just a different application. Series versus parallel. Those are the two types of single duct VV applications. Now, we talked about, when we talked about air handling units, we talked about double duct. Not generally used today. A lot of buildings, a lot of hospitals out there still have it. So I would have a cold duct and a parallel hot duct above the ceiling. And I'd have to branch off that VAV box with my two branches, and essentially got an internal two VAV boxes. Air mixes, goes back out to space. Got the same application. You're measuring airflow here, you're measuring airflow here. You got a motor. You got a motor on each one of those. Some mixing chamber, the air goes out. What you have here is, could be variable volume, could be constant volume. You've got a thermostat in space that says I'm hot, I need cold air. So generally the hot duct might close completely through the controller, and the cold duct opens to its maximum position. I got 400 CFM out here cooling. Thermostat gets satisfied, goes to its minimum of 100 CFM. There's a little programming problem right there. Which one do I use for minimum CFM? Generally, and this is open to the type of design, generally the outside air is connected to the cold duct. Because in this air handling unit, the way it's constructed, I've got remember I had a kind of a twin airstream. One was hot, one was cold. I had cooling coils and heating coils. What does a cooling coil do? It dehumidifies. So in the summertime, I've got hot and humid outside air. I've always got to make sure it goes across the cooling coil to get it dehumidified. So generally, your cold box is going to be the minimum airflow. This is always going to remain closed until I need heating. So what happens when I need heating, this box closes to its minimum position of 100 CFM. This airflow makes up the difference to get up to 400 CFM. So that's how a dual duct block switch works. That's generally open to how the system was designed, where the outside area is. But you can see that it offers some programming issues on these, how to maintain minimum airflow. Most cases in the old hospitals, these are just constant volume. But they can be retrofitted to variable volume applications. In a constant volume application, this would just open and close, depending on what thermostats. I'm either calling for heating or I'm calling for cooling, or space is somewhat satisfied. So these boxes, these 2 dampers, open and close to maintain temperature and space. Each one may be halfway open when the space is actually satisfied, if I were at constant volume, which a lot of hospitals, the PAV terminal is constant volume. So that's a double duct. It's basically just 2 single duct VAVs, no need for reheat because it's got hot air and cold air. Again, you got a thermostat, got a controller that talks, you're measuring the airflow. Okay? So that gets the majority of the type of VAV box applications. Anybody don't have a handle on how they operate? Let's talk a little bit about...
Question.
Yes, sir.
What would be the advantage or disadvantage over the parallel VAV as compared to the series VAV setup? Or is there any?
The only advantage of the parallel is that I could actually shut this off and recirculate all the air through the space for heating.
You saving more?
For instance, if I had a separate ventilation air system, which probably not likely, but that would be the only thing that I can think of. Because here, well, either way in the series, you've got this capability here, but I've never really figured that out myself.
Okay.
I'm sure there are reasons to have a series. You don't see a series a lot. Because in the series, well, I guess I can't tell you what the difference is. In the fan power, in the summertime, I'm utilizing this airstream right here. I'm utilizing that pressure right there to get the air into space. The fan's off. In this box, this is the outlet.
Okay.
So that fan always has to run, even in the cooling mode.
Using more energy with the series then.
Well, I would assume that I'd have a lot of pressure here and I need that fan to take care of this, or I can subtract that pressure with this fan right here.
Cost a little bit noisier too.
Could be a little bit noisier, but the problem is that fan is generally a lot more efficient than that fan right there. So that's why you see mostly parallel operation. Because why run that fan in the summertime? Because that motor is going to generally a part winding motor operating at 50 or 60% efficiency. This is a larger motor operating probably 75, 80% efficiency, maybe even more. So that's one reason in the series. That's always running. This is only running in the wintertime.
Steve, would they use a series fan power in a kind of a retrofit where they want to put more boxes in or something without changing the air handler to give you more flow in that area? Or
But like I said,
would that make sense?
this would add additional static pressure to operate all this ductwork down through here. If this fan didn't have enough pressure on it, then you could use a series fan power box. If you're, say, converting a single zone to a multi-zone or single duct VAV application, that could be some application. Normally, the air handler gets changed out in a total retrofit like that. Let's talk about a little bit about airflow in space. So I got a ceiling here. And I got a grill. And I've got that return either ducted or open to a plenum. Grill there, grill there. I just wanted to mention a little bit about diffusion in a space and how that's supposed to be done. The idea of getting airflow into a room is the intent is for this air, whether it's 55 or 120 degrees, is to be introduced into the space like this, go down along the wall and diffuse into the space. The reason for that is in the summertime, this is 55 to 60 degree air. If my desk is right here, and I'm sitting at that desk, I don't want that air dumping on me. It creates a draft. So a proper diffuser, and these right here, in my opinion, are the only proper diffusers for a variable volume application. Send that air along the ceiling, it gets mixed with the room air, so by the time it starts going down the wall, it's close to room air temperature. But I'm still moving that much airflow through the space and then back out to the return, so I'm meeting my demand. That's the intent of the diffuser, is to mix with the airflow in the space so that you don't feel drafts. Now the worst diffuser that you can use right there, can anybody guess what that is? Perforated face diffuser, which is used 99% of the time. That air will just simply, cold air will just fall right to the floor. And it's probably our portion of our fault, not informing engineers properly, but a good gentleman named Hank Wade Sr., 30 years ago, told the engineering community perforated face diffusers were the things to use in this newfangled VAV systems. And of course, Hank was God to most of the engineers. And at that time, maybe that was all that was available. But that's not what is available now. There's various versions of this. But you can see these diffusers in various manufacturers like Kruger and Titus and Tuttle and Bailey. See it tested. No matter what the air temperature is, 55 or 100, that air gets pushed along the ceiling and diffused. They'll do smoke pattern tests. When you do a smoke pattern test on VAV diffuser, especially even the hot air just doesn't know what to do. It still doesn't move along the ceiling. You see some manufacturers put different types of diffusers above the perforated plate. It just doesn't help. But that's all I wanted to mention was that this, in an air conditioning space, the intent is to move the air along the ceiling, diffuse into the space, become with the same temperature as the room before you get into contact with your skin. So it's not drafted. Same way on the heating side. It's very difficult to push hot air down. As long as you can push it along the ceiling, get it diffused with the space, get it back to that room temperature, and it'll circulate through the space. And the intent is to do something like this. Get that air moving like that and back to the return. So that you get good circulation throughout the entire space.
What can you do on a floor mounted type?
Well, a lot of especially we didn't talk about that, the underfloor distribution systems. What the underfloor people do, now there's in a residential application, you just have floor diffusers. And I guess in some commercial applications, you have a floor diffuser. The thing to do is get along the perimeter, get it away from the furniture, but you never know where the furniture is going to be. Now, in the underfloor applications, like over at Heifer, I'm sure there's some more around here, but what they do is they put the cold air into the plenum. They have something like a VAV box. It's a very simplified VAV box. They dump it into that floor plenum at very warm air temperature. They do all the dehumidification that they're going to get. And what's delivered to the space is generally about 60 to 65 degrees. And they use a special type of diffuser that gets a very swirling application. But what they want to do is deliver as warm air in the cooling system as they possibly can in the summertime. As close to room neutral as they can. So you're moving a lot more airflow, but at a higher temperature, to try to eliminate those drafts. And what they do, the reason, you know, take a space like this, just like we're in right now, and do a temperature gradient. For instance, in the summertime, I may have 60, 58, 55 at the grill, and go the temperature gradient. They'll do a temperature gradient like this and see what the temperature is, and they're trying to maintain 74 degrees right here in the comfort zone of your head and torso. And the reason you try to get that air mixed is because when you get down here, you still want it to be very warm because you don't want a cold floor. And what happens in the underfloor system, they got this spiraling airflow like this. And all it does is come up and mix into the space. So they have to have as warm a temperature as they possibly can because you don't want the cold floor again. I'm not real familiar with underfloor systems. There's only a couple applications. But there is a lot of engineering, there is a lot of study on it. It seems to work. The reason for the underfloor application was that the theory was in modular office buildings, everybody creates a cubicle. And you move quite frequently. And the cubicles would be torn down, the people would move to the new space, the cubicles would be rebuilt. And so you got this modular underfloor system which you could just pick up diffusers and move around. But what happened was the people moved to a different space, but the cubes stayed the same. So the idea of the underfloor system really hasn't picked up yet because the cubicles are so expensive. And you're just moving to another space, and usually the cubicle layout's the same. So that's generally why you're not seeing a lot of underfloor systems. Any other questions about VAV boxes? Nope. 7:45. Time to go to work. Okay. Reciprocal, that is 0.43. A little easier, just multiply 60 times 0.43. Okay, that's kind of the number we picked out the other day. 25.8 is my static head. Now, I also want to make sure that I've got at least some positive pressure up here in case like in a bore application, you may have something go haywire, and up here we've got 212 degree water. So you want to make sure that you've got positive pressure up here in your piping loop so that you don't flash the steam. So if I've got a static head of 25.8 psig, I'm generally going to add at least 4 pounds to that as a safety factor. Make sure that I've got positive pressure up here at the top of my system. So I'm going to size this relief valve in a 60-story building with a mechanical, with a valve down here in the basement of maybe 30 pounds. Now if I moved that valve up to here in the penthouse, I have no static head above it, so I could buy the standard 12-pound valve that you go down to the R&D and buy every day. So that, not only do you need a static head, put a little safety factor on there. Okay. Appreciate you guys coming. We'll be here Thursday.